ourselves to looking at how do you do the phasor version for an inductor, and this is going to be a bit more involved here. Now we see that V is equal to L di dt in the regular time domain, and we want to convert this to phasors here. So we need to see how this is going to work. Well, the idea is if your I of t is, I don't know, some amplitude times cosine omega t plus some other amplitude sine omega t j, right? Or we can write it in the easier way in the polar notation r e to the j omega t is what we're going to have. Well, if I take the derivative of that, then I prime of t, the r stays the same, e to something goes to e to something, then multiplied by the derivative of what's inside with respect to t, we're going to get this j omega here. So what that means is di dt is the same as your original I, but then multiplied by j omega. So that means that if I have V is L di dt, then in phasor notation, my phasor V is L times j omega phasor I. This is how we're going to write phasor I here. And so that means that the thing that needs to be the z here is this initial coefficient. So for an inductor, your impedance is j omega L. So if we're going to convert an inductor into a phasor inductor, we need to have j times omega times L. And I want to point out something that's incredibly important here, that is including the omega, the angular frequency of what we're doing in our circuit. And so what that means is if you have a circuit at, say, 1 radian per second, and then you take a circuit at, say, 5 radians per second, the impedance of the second circuit is going to be 5 times as large as the impedance on the first circuit. Your impedance depends on the frequency of your circuit. And that's going to be actually a very, very important point in Chapter 14. It's not something we worry about too much in Chapter 9 and 10, and the reason why is, in a given problem in Chapter 9 and 10, you only have one frequency and that's it. So you don't have to worry about that. You just use the frequency they give you, and it's not a problem. But we are going to see in Chapter 14 where we're going to have different frequencies, and it's important to know how things change when you change the frequency. Okay, so we have that then. So that means if we take our regular circuit and convert it to phasor, now we have the impedance j omega L. And if you were to graph that, then when you multiply a complex number by j, it's going to have a 90-degree shift. And the reason why is, this is something that you can go ahead and check, is e to the j 90 degrees, or in other words, one angle 90 degrees is the same as j. So when you multiply by this number, we said you add the angles, so you add 90 degrees. And so that means in our graph here, whatever angle the current is currently at, the voltage is going to be 90 degrees higher angle than that. And if you draw your graphs over here, you'll see that the voltage reaches its peak before the current does. And the reason why is, again, that the angle of the voltage is always 90 degrees more than the angle of the current. So if it wasn't going to reach the peak until a certain point in time, the voltage is going to get there first because, again, you are 90 degrees ahead of time. Another way of thinking about it is, you know how you look at your functions, and if you add a number inside, it shifts the graph to the left? Well, we're adding 90 degrees inside, so it's going to shift the function left. Now, we say that the voltage we say it leads the current. Or we might also say that the current lags the voltage. So these are just ways that we talk about the same thing here. But just remember that for an inductor, the voltage leads the current. And there's a physical way of thinking about this, and that is that you know that if you have an inductor, you know that the current cannot change instantaneously. So if you were to apply a new voltage source to this inductor, the voltage would change right away, but the current would take time to catch up to it. Or in other words, the current is lagging behind the change due to the voltage. The voltage leads the current lags the voltage. So the end result of all of this discussion is that when you have an inductor in your circuit and you want to convert it into a phasor, you use Z is j omega L.